Welcome to Module 7, talking about equations of state. Now, this should be the first material that you didn't really cover all that thoroughly in a general engineering thermodynamics course. Our goals here will be that by the end of this module, you ought to be able to distinguish between the three main categories of equations of state: cubic, empirical, and theoretical. And if you were given all of the information to solve one of those, you should be able to work with the equation. But we want you to go a little bit beyond that for the cubic equations of state. You should be able to model a liquid, vapor, gas, or supercritical system using a cubic equation of state, where you are going to need to compute the values for the adjustable parameters and then solve this cubic equation and correctly interpret the results when there are multiple solutions. So, all of this talk, what on earth is an equation of state? An equation of state is simply a mathematical relationship that allows one to calculate thermodynamic properties for the state of any particular substance. Now, most of the equations that we see are going to relate pressure, volume, and temperature. But we actually can relate any of our thermodynamic properties in an equation. So we will in the future also relate U, internal energy, H, enthalpy, A, the Helmholtz energy, G, the Gibbs energy, and even S, entropy. So we will be developing a much broader sense of what an equation of state is very soon. One thing I do want you to note, equation of state is just quite a mouthful and it's really a pain in the neck to write all the time. So you will see that a lot of times we will abbreviate this as an EOS. So you've probably been introduced to the compressibility factor, but maybe this is new. So what happens is we can take that ideal gas law kind of concept and take the specific volume version of it. So I divide both sides by number of moles, and then PV equals RT is the ideal gas law. But we know that things aren't really an ideal gas, so what people have done is they have created a dimensionless group. So something that has no units by the time you complete the math. And if it has no units, then it's not going to matter whether I work in, degrees Fahrenheit or degrees centigrade, as long as I am appropriately using the equations. Okay, so I can use any system of units. In our case, what we're going to do is a ratio of PV over RT. So since PV equals RT was the ideal gas law, we know that the equations are going to have the same units on both sides, so therefore PV over RT will be dimension-free. Now this is our compressibility factor, and it has historically been denoted with a Z. If I have an ideal gas, Z is equal to 1. But for real substances, it's going to be more complicated. So the graph that you see here is the compressibility factor of methane. And across the bottom axis, we have the pressure. And across the vertical axis, we have Z, the compressibility factor. And then this relates to various values of temperature along all of these various curves. So each one of these curves represents a different temperature. And so if I knew the pressure and the temperature, I could find my pressure, go straight up, find the temperature, and then reading straight across would give me a value of the compressibility factor. Now, what people noted was that it really didn't matter what the substance was. All of the graphs kind of ended up looking quite the same. So people started studying these things and trying to predict behavior. So the first category of equation of state that we're going to look at is the virial equation of state. It is purely theoretical. It's based on statistical mechanics theory, and you'll learn a little bit more about that if you take physical chemistry or the molecular thermodynamics course. They're going to talk a lot more about the theory behind this. But basically, a virial equation of state is going to be an infinite series in either pressure or reciprocal volume that is going to take into account all those reasons why a real gas is not ideal. So a real gas, the molecules are not infinitesimally small. In a real gas, the molecules are not perfectly round. In a real gas, molecules interact with each other. And so if you take all of those effects, we can predict, based on shape, size, interaction, what the behavior might be. So this is the virial equation of state, and it's just simply an infinite series. Now in practice, when we use this, we usually truncate it after just a few terms. And we name the terms and name the coefficients in terms of their position in the sequence. So 1 is the first virial term. BP, or B over V, is the second virial term. So therefore that B, or B prime over RT, either of those are equal to each other, is what is going to be called the second virial coefficient. And the third term with the C, that's going to be the third virial coefficient. B is fairly well understood for an awful lot of chemicals. C, for not quite so many, but this is a growing area of study. So usually we just take as many terms as we feel like we need, and what each term is really trying to tell me is how the molecules are going to interact. So in the first terms, it's when one molecule is all by itself. That's why it's just a 1. The second term is when 2 molecules come together at the same time. The third term where 3 molecules come together at the same time. Now, if I were to do the fourth, that would mean I'd have to have 4 molecules at the same time. Think of the 100th term, 100 molecules all coming together at the same time to interact simultaneously. Those are going to be more and more rare events, especially in a gas. And so, most of the time, especially when I'm studying gases, I can get away with only using the first 2 or 3 terms. Now, the next major category of equations of state is the cubic equation of state. Cubic equation of state is going to be so named because it's going to be third order in volume. These are generally classified as semi-theoretical. The virial equation of state was theoretical. This is semi-theoretical. It's based on some theoretical principles, and then we just have to kind of use our judgment, I guess, almost. Some scientists have gotten together and studied all sorts of data and come up with what seems to work with some theory thrown in. Now, the first one of these was 1873. It's van der Waals. He is actually a Dutch hero. He's from the Netherlands, and so if you want to come by my office sometime, actually, you can see I have a Christmas card that one of my friends from the Netherlands sent me with van der Waals' image on the front of this Christmas card. So he's very important because this was really the start of a huge new area of working with chemicals and modeling chemicals. What he recognized was that some really small changes to the ideal gas law could make a huge improvement in the performance of that equation. So he added an A term, if you see down here below, A over V squared, and that term accounts for interaction between molecules, very similar to the virial equation of state. He also added a constant B that is supposed to account for the fact that molecules actually take up space. They have a volume. So the result is P equals RT over V minus B minus A over V squared. So we're going to pause here at the van der Waals equation of state. We're going to come back and study the cubic equation of state in a bit more detail in the next video.